has 2 electrons. The first one is just like hydrogen's, and the second one is right there with it, in the same level and sublevel. So for helium, it's on row 1 of the S block, and it's in the second column. So row is 1, block is S, column is 2. And that's exactly what we got before using that other chart. Do you see kind of how this works? All right. Now, going back to this other diagram for just a minute. Energy level 1, S. Energy level 2 at S and P. Energy level 3, S, P, and D. Level 1 has 1 part, level 2 has 2 parts, level 3 has 3 parts, etc. There was no such thing as 1P, correct? P first comes into existence on level 2. And so the top row of the P block is not 1. It's level 2. There's no such thing as 1P. So the top row of the S block is 1. The top row of the P block is 2. The top row of the D block is 3. Which means when we're going in numerical order here, look what happens. Sodium and magnesium, we're putting electrons in the 3s. We stay in order by atomic number, 13, 14, 15, 16, 17, 18. Those are all in the 3p. 19 and 20 are in the 4s, and then we come back for the 3d. The top row of the D block is level 3. That's exactly the same glitch that we had on that other diagram, correct? But you don't have to remember where all these little glitches are because it's all coded into the chart for you. If you remember, it's SPDF starting as rows 1, 2, 3, 4. Then you're going to throw electrons into the 4s before you do the 3d. Just chronologically by atomic number, you have to. And so all those little exceptions are coded in there for you. It's just a matter of labeling the periodic table correctly before you start. The F block begins as level 4. So this top row in the F block is level 4, and the row below is 5. Using that chart, do the electron configurations for oxygen and potassium and arsenic. These are already in your notes because we did them a few minutes ago by the other charts. Try them now using just the periodic table. For oxygen, there's 8 electrons to be accounted for. The first 2 are just like hydrogen and helium. So, first row of the S block, you've got both of those. That's electrons 1 and 2 for oxygen. Where are electrons 3 and 4? Second row of the S block has your 3rd and 4th electrons, right? Where are electrons 5, 6, 7, and 8? Second row of the P block, right? Technically, that's second row. There is no first row. So second row of the P block, and it's in the 4th column, correct? So it's got all 4 of those. And 2 plus 2 plus 4 is 8, and you know you've got everybody accounted for. Do you see how to read that off the chart? Yes? No? Yes? Okay. Potassium, there's 19 electrons. The first 2, I'm just going to scribble this below it. The first 2 electrons are in the 1s. The 3rd and 4th are in the 2s. The 5th, 6th, 7th, 8th, 9th, and 10th, where are they? 2p. 5 through 10. Where's the 11th and 12th? 11 and 12. 3s, 3rd row of the S block, right? Where are 13 through 18? 3p, 3p6. And then there's one more, electron number 19, 4s1. And that's where you stop because you've reached the symbol for potassium. And then yes, go ahead.
What about the 3D?
The 3D?
Yeah.
You don't have that for potassium. The 3D comes in after the 4s. You stay in order by atomic number. Arsenic then. Now with arsenic, you do get into that's not done yet. But with arsenic, you put these into the 4s, that's your 19th and 20th. Then 21 through 30 are in the 3D, third row of the D block. And then you get back to the 4p. And that's where you wind up. Okay. All right, now I just gave you an unmarked periodic table, such as you will have on your exams. And hopefully, when the day comes for exam 2, then the very first thing you'll do before you even look at the test, as soon as this periodic table hits your hand, you'll go S, P, D, F, and starting them on row 1, 2, 3, 4. Hopefully. Because that's the key to doing these configurations. S block starts at level 1 and works its way to higher numbers. P block starts at level 2 and works its way to higher numbers, etc. That's the pattern. So benefit number 1 of using the periodic table is you don't have a scheme that you need to memorize. You don't have to memorize that 4s comes in before 3d or 3d or anything like that, because it's all laid out there for you. It's also a benefit that it works for all the elements, not just a few of them. But another benefit of it is that based on the periodic table, we can start dealing with what's called abbreviated configurations. Because even with one like arsenic, that was getting pretty long. You don't want to do uranium like that with 92 electrons. That would take up 2 lines of paper probably. It would be nice to be able to abbreviate them. And using the periodic table, you can. And for abbreviated ones, just look back at potassium and arsenic. When you think about bringing atoms together, we take this atom, so we rub it up against this atom. We said before that it's the electrons that make contact and it's the electrons that react, but it really isn't even all the electrons. These that are on the outer layer are going to make contact and react, but these that are down on the interior never see the other atom. Those are interior layers, and therefore they're unreactive. So the key to doing these abbreviated configurations is by abbreviating in brackets what's considered a noble gas core. Find potassium on the periodic table. That's number 19. And count backwards numerically until you come to a noble gas. That would be number 18, argon, right? 19, 18, backwards and so forth. So you can abbreviate potassium's configuration as saying it has an argon-like core of electrons. And that abbreviates the first 18 electrons. And the key here is, you know that noble gases don't react. They don't form compounds. They're inert. And so the reason we're using those, the noble gases, as our abbreviating tool, is that we're indicating not only are these 18 electrons arranged just like argon, but they're every bit as unreactive as argon. We're abbreviating the interior, unreactive, practically irrelevant parts of it so we can focus on what's on the exterior. This abbreviates the first 18. Where is your 19th? Fourth row of the S block, first column. So this is the abbreviated configuration for potassium compared back to what we had before. You always abbreviate in the form of noble gas. And that's called your unreactive core of electrons. The core electrons are the ones that you are absolutely certain will not react. Never, never, never. Arsenic is element 33. Count backwards by atomic number until you come to a noble gas. Who's it going to be? Argon still. And that abbreviates 18 electrons. Where are the 19th and 20th? 4s. 21 through 30. 3d. 31, 32, 33. And that's a whole lot shorter than what we have been doing. And it emphasizes this exterior stuff and minimizes what would be considered the core. And that way you don't have to start all the way at hydrogen every single time. You can start at something that's a noble gas and just add on the exterior things. It makes it a lot shorter, a lot quicker, and it emphasizes what's important. But the key is to always start with a noble gas as your core. Question with that? All right. Now we're ready for uranium. Find uranium on the periodic table and count backwards by atomic number until you find a noble gas. .92 electrons to be accounted. backwards, who's your noble gas? Radon. And that's our core, and that abbreviates 86 electrons, correct? The first 86 electrons are arranged just like radon and known to be unreactive. Where's the 87th and 88th? 7s. Where's the 89th? Where's the 90th, 91st, and 92th? 5. F. 3. And here we started the 6D, but we didn't even finish it before we moved on to F. It gets glitchier and glitchier as you go up. And that experimental chart we had up here didn't even predict that. But the periodic table does. But again, that's not something you need to remember, because as long as you stay in strict order by atomic number, it's going to lead you to that. We're not reading left to right across the page, because that would be 87, 88, 89, 104. Right? You're going by atomic number, and you place things by atomic number. And so we go 1 electron into the 6D, but then the table tells you to move on to 5F, and sure enough, experimentally, that's what happens. Don't ask me why it happens. Right? It's a known pattern, but there's really not a good explanation for that as yet. But that's what it does, and the chart tells you that's what it does. Question about that? Do the configuration, abbreviated configuration for osmium. You should be starting with a xenon core, and that abbreviates your first 54 electrons. 55 and 56 are in the 6s. Number 57 would be in the 5D. But where is 58? 4F. And 58 all the way through 71 are down there in the 4F, correct? Okay. Now this next thing I put up here, don't write it down. 72 through 76, we're back into the 5D again, right? And 72, 73, 74, 75, 76, that's 5 more electrons, that's what they would be. Going strictly by the periodic table, this is what you would get. And that's correct, except that this 5D and that 5D are the same sublevel. And so you need to condense it down. And it doesn't matter whether you condense it before or after the 4F, as long as you do condense it. By the time you're done, that needs to be 5D6. If you want to put 5D6 before the 4F14, that's fine. Or if you want to put 4F14, then 5D6, that's fine. As long as you're showing 5D only once, and that there's a total of 6 electrons in it. You put in the 1, you go off and do the 4F. Once that's full, you go back for the rest of the 5D. And you do wind up with 6 electrons there, and you check that because osmium is in the 6th column. It's in the 6th vertical column of the D block. And this is what we would get as the final configuration. Question with that? Yes?
You can replace the XD instead of the rest of the numbers in the beginning?
Yeah. Instead of starting at 1s2 and working our way up, we're just starting with a noble gas.
In the exam we can do that?
And abbreviating that. That way we don't have to show all the interior stuff. Question about that?
Why does 4 go after the 5? Oh, it's...
The 4F after the 5?
Yes.
I'm just in the habit of putting this before, but if you're going, the reason you start the 5D and then finish it after the 4F is going by your atomic numbers. I mean, that's not something you should try to remember, okay? Because as long as you stay in strict order by atomic number, it will tell you that. All right. We've defined core electrons. There's a couple of other categories here we need to define. Core electrons are the interior ones. The ones that you are absolutely certain will not react. There's another category called valence. And these are outer level S and P electrons. And that's the other extreme. Those are the ones that you are absolutely certain will react. So looking over here at potassium's configuration, it has 18 core electrons, and this one, which is outer level and S sublevel, is specifically these sublevels. That's one valence electron. These 18 will never react, but that one will. For arsenic, how many core electrons? This is core. How many core electrons? 18. How many valence electrons? 5. Outer level's level 4. This is level 3. Level 3 is not outer. Okay. Plus, that's a D. And D's don't count as valence ever. It's specifically S and P sublevel. So this is 5 valence electrons. And that leaves you with these, which are cleverly categorized as other electrons, because they're neither core nor valence. Sometimes they react, sometimes they don't. It just depends upon the situation, it depends upon the element. Sometimes they react and sometimes they don't. But core and valence are your two extremes. Go ahead.
So are valency electrons always the electrons that will be lost or gained in a reaction?
Yes. Every now and then these others will get involved, but it's not often. Look at osmium's configuration. How many core? 54. How many valence? 2. Uranium over here, how many core? Well, 86, I already got that up here. How many valence?
2.
2. D's and F's never count. D's and F's are never valence. So only 2 valence electrons for uranium. Question with that? All right. Write up abbreviated configurations for these elements. What you got. All right. Argon is a noble gas. Noble gases are distinguished in that they are resistant, extremely resistant to reactant. And structurally, the reason for that is this. This is core, those are valence. The 3s is just a single sublevel, but it's filled. The 3p is 3 orbitals having 6 electrons, that's filled. Everything it's got as valence is perfectly and completely filled. Experimentally, that makes it extremely stable. How many electrons does it take to get that full? 2 plus 6 is 8. So there's this thing called the octet rule, octet being a group of 8, that atoms are more stable when they have 8 valence electrons. More stable when valence is full. Atoms are more stable when they have the valence shell filled, and it takes 8 electrons to get the valence shell filled. So that's why argon is so unreactive. But now look at chlorine. Does it have a full valence? No. No. chlorine is a nonmetal, and as far as reactions go, nonmetals gain electrons. So specifically, how many electrons does it need to gain to have that full valence? 1. And so, whereas chlorine has 7 valence electrons, the chloride ion, after it gains 1, would be this. Correct? Adding 1 electron to what chlorine already had, and that looks suspiciously similar to argon's configuration, correct? And by similar, I mean identical. Do you see that that's identical? Chlorine by itself is extremely reactive, but the chloride ion, Cl negative, is extremely stable. And the reason it's so stable is it's built like argon. And it's got that complete octet. Chlorine forms exactly and only a -1 charge because 1 is exactly and only what it needs to get there. It's not going to gain 2. You will never, ever in your life see chlorine as a -2 charge, because what's it going to do with 1 more? It's got the octet already at that point, correct? That's not going to happen. It gains precisely 1 because that's precisely what it needs to become argon-like. The term here is isoelectronic. Isoelectronic means same configuration as. The chloride ion is isoelectronic with argon. Cl negative is isoelectronic with argon because it has exactly the same configuration of argon. Sulfur is also a nonmetal, and so its tendency is to gain electrons. But how many is it going to gain to become stable? Apparently 2, right? Because 2 would give it the octet. And so sulfur always forms a -2. To give you this configuration. Just like you'll never see chlorine as a -2, you will never see sulfur as a -1. If it's not stable with S2P4, it's not going to be stable with S2P5 either, right? But it's going to do what it needs to do to get the octet. And it takes 2 additional to get that octet. This is what we're talking about as the octet. Valence full at 8 electrons. So based on that pattern, what charge would you predict for phosphorus? 3 minus. Because it needs 3 more. Chloride, sulfide, phosphide, those are all isoelectronic with argon. Yes?
If you were asking for a question in the test, or a question like the test, would we just put the 3 minus and then write it as its original form, or would we go ahead and make it an octet?
What I've got over here is the configuration for elemental phosphorus. And this is the configuration for 3 minus.